Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring some of the strangest places in our universe. Rare galaxies that seem to break the laws of physics and challenge our best theories about the cosmos. Some shine with unimaginable energy, while others are older than what we thought was possible, and some of them look almost unreal, as if space itself decided to play by different rules. The more astronomers discover, the stranger these vast islands of stars become. They may appear calm at first glance, but immense cycles of creation and destruction lie just below their surface. A galaxy may be shaped by gravity, by dark matter, or by hidden forces that we are only just beginning to understand. And far away, in the farthest reaches of the cosmos, even stranger galaxies begin to appear. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your eyes to grow heavy. And as your mind begins to gently unwind, join me as we explore our fascinating cosmos together. Let's begin. Some galaxies shine brightly not because of stars, but from the black holes at their center. That sounds backwards at first. Black holes are famous for swallowing light, not producing it. But the darkness itself is not what shines. The brilliance comes from the material spiraling inward. Gas and dust can be whipped into a blazing disk that grows so hot it pours out radiation across the spectrum. In some active galaxies, that central region becomes brighter than the combined glow of billions of suns around it. Astronomers call the most extreme examples quasars, and they can be seen from astonishing distances. What makes them so gripping is the contrast. A whole galaxy, with all its stars and clouds and structure, can be visually dominated by a single feeding point at its heart. When you look at one of these objects, you are not just seeing brightness. You are seeing gravity turned into light on a scale almost too large to absorb. The strangest galaxies look broken, twisted, ringed, or lit from within. The old picture of a galaxy is neat and orderly. You imagine a graceful spiral or a smooth, glowing oval drifting in silence. Then, astronomy shows you the oddballs. Some look as if their arms have been pulled loose. Some carry bright rings around empty-looking centers. Some seem lopsided, bent, or scarred, as though they remember an impact. Others have such fierce activity in their cores that the light seems to come from the inside out. These shapes are not decorative accidents. They are clues. A twisted disk can point to a past encounter. A ring can mark a violent passage through the center. A bright core can reveal matter falling toward a black hole. Strange galaxies are fascinating because they refuse to be background scenery. They look like evidence left at a scene. The moment you notice that, each weird outline stops being a shape and becomes a story. A galaxy can keep forming stars long after it should have gone quiet. Astronomers once imagined a fairly clean divide. Some galaxies were lively and blue, full of young stars. Others were older and red, with their busy days behind them. Real galaxies turned out to be less obedient. Some that seemed settled and aging still managed to spark new rounds of star formation. Fresh gas may drift in from outside. A small companion may be swallowed and deliver new material. In other cases, gas that was heated or disturbed can cool again and collapse into stellar nurseries. That means a galaxy does not always follow a one-way path from youth to retirement. It can stall, revive, or surprise observers with pockets of renewal. This is one reason strange galaxies are so compelling. They blur categories that seem simple from a distance. Even after billions of years, a system that looks finished can still find enough raw material to light new stars into being. Some galaxies are still colliding in slow motion across millions of years. The word collision sounds sudden, almost explosive, but galactic encounters unfold with enormous patience. Two vast systems can begin tugging at each other long before they fully merge. Their shapes stretch. Their gas clouds are disturbed. Their stars are flung into long arcs and tails. All of this can continue for ages beyond any human timescale. The antennae galaxies are a famous example, caught in the act of intertwining while great streams of stars extend outward like thrown sparks. What makes these events so strange is the contrast between violence and slowness. The consequences are dramatic, yet the process itself is drawn out over millions or even billions of years. A galaxy can look torn open while the interaction is still unfinished. When astronomers observe one of these scenes, they are not seeing a single moment of impact. They are seeing a long gravitational argument still working toward its conclusion. There are galaxies shaped like wheels, needles, cigars, and glowing bubbles. Once you start looking beyond textbook spirals, the variety becomes almost playful. The cartwheel galaxy really does resemble a wheel, with a bright ring surrounding a more compact center. EJ-on-spiral galaxies can appear as thin as needles because their flat disks are seen from the side. Messier 82 is often called the cigar galaxy, thanks to its long, narrow form. Other systems seem puffed up or rounded in ways that make them look like luminous bubbles suspended in darkness. These shapes are not just amusing labels. They help people remember that galaxies are physical structures with real orientations, histories, and internal motion. Change the viewing angle, and a familiar type can look completely different. Add a collision, a burst of star formation, or a cloud of dust, and the appearance changes again. The result is a universe full of forms, but feels surprisingly concrete, almost as if they could be held and turned in the hand. One strange galaxy has a ring that circles it like a cosmic target. Hoag's object is one of those sites that feels designed rather than discovered. At the center sits a round yellowish core of older stars. Around it, separated by a dark gap, lies a nearly perfect blue ring where younger stars shine. The symmetry is so striking that people often mistake it for an illustration or an optical trick. It is neither. It is a real galaxy, and astronomers still debate exactly how it formed. One possibility involves an ancient interaction that reorganized its material. Another idea suggests internal dynamics shaped the ring over time. Either way, the fascination comes from how improbable it looks. Most galaxies wear their history in messy asymmetry, with warped arms, dust lanes, and uneven patches of light. This one appears composed with almost unsettling precision. It is a reminder that the universe does not only produce chaos. Sometimes it produces order so clean and improbable that it seems almost impossible at first glance. Some galaxies spin the wrong way around their own inner stars. In a familiar system, you would expect the stars and gas to share the same overall direction of motion. Strange galaxies sometimes break that expectation. Astronomers have found cases where gas rotates one way while a central population of stars moves the other way. In more extreme examples, whole stellar components seem to be counter-rotating within the same galaxy. That is a powerful clue that the system did not grow in a simple, isolated way. It probably acquired material from outside, perhaps by drawing in gas from its surroundings or by merging with a smaller neighbor. Instead of blending neatly, the new arrival kept its original motion and left a kinematic scar. This is fascinating because the oddness may be invisible in an ordinary image. The galaxy can look calm and balanced until spectroscopy reveals the hidden choreography. then the picture changes completely. What seemed serene becomes a record of an encounter written in motion. A galaxy can hide most of its mass in something we cannot see. This is one of the great shocks of modern astronomy. When researchers measure how fast stars and gas move inside many galaxies, the visible matter does not seem to provide enough gravity to hold everything together. Outer regions often orbit too quickly. By ordinary expectations, they should fly apart. Instead, they stay bound. The leading explanation is dark matter, an unseen form of mass that does not glow, absorb light, or appear directly in a telescope image. Its presence is inferred through gravity. In some galaxies, especially diffuse ones, the hidden component seems to outweigh the ordinary stars and gas by a remarkable margin. That means the bright, beautiful structure we admire may be only a small, luminous trace inside a much larger, invisible framework. Strange galaxies make this even more vivid, because their odd motions and distorted shapes can expose the influence of matter we cannot observe in any conventional way. They reveal absence, acting like a force. Strange galaxies reveal what happens when gravity gets wild and messy. Gravity is often introduced as a tidy rule. Massive things attract other massive things. In real galaxies, that simple principle can create astonishing complexity. A close pass can pull out tails of stars thousands of light years long. A merger can scramble elegant spirals into chaotic clouds. Gas can be compressed into furious star-forming regions, while other material is thrown outward or funneled toward the center. The result is not random. It is the consequence of countless objects responding to each other's pull all at once. That is why strange galaxies are so revealing. They let astronomers watch gravity not as a diagram, but as a sculptor working at enormous scale. In these systems, you can almost read the forces directly from the shapes. Curves, bridges, ripples, and warped disks become visible records of motion and stress. The weirdness is not a distraction from the physics. It is the physics made visible in all its unruly grandeur. Even our own Milky Way may carry scars from ancient galactic wrecks. It is easy to imagine strange galaxies as distant curiosities that belong to some other corner of the universe. The Milky Way is a useful correction. Our home galaxy appears fairly orderly from the outside, yet evidence suggests it has had a turbulent past. Streams of stars arc through the halo, and many of them are thought to be the remains of smaller galaxies torn apart and absorbed over time. The Sagittarius dwarf galaxy is one of the best-known examples, currently being disrupted as it passes through and around the Milky Way. Other structures in stellar motion hint at ancient mergers that helped build the galaxy we live in now. Even the thick disk and halo may preserve traces of those long-ago encounters. That changes the perspective in a lovely way. The story of strange galaxies is not only about rare monsters far away. It is also about the deep history of our own cosmic home. Hoag's object looks like a golden eye staring through space. Few galaxies look so deliberate. At the center sits a round cluster of older yellow stars. Far around it floats a crisp blue ring where younger stars shine in a near-perfect circle. Between them lies a darker gap that makes the whole object seem almost unreal, as though someone painted a pupil, an iris, and an empty border on the black sky. That appearance is what makes it unforgettable, but the real fascination is that astronomers still argue about how it came to be. A past collision is one possibility. Slow internal reshaping is another. Neither explanation feels completely satisfying, which only adds to its pull. Most galaxies wear their histories in visible disorder. This one seems to hide its violence behind elegance. It reminds us that the universe can be strange in more than one way. Sometimes the oddest sight is not chaos, but a calm pattern that should hardly exist at all. The Cartwheel Galaxy was blasted into shape by a galactic collision. Its name is wonderfully literal. The bright outer ring really does look like the rim of a wheel, while the inner region suggests spokes and a hub disturbed by impact. Astronomers think this form was created when a smaller galaxy plunged through a larger disk galaxy, sending a powerful ripple outward through gas and stars. That ripple compressed material as it moved, which helped ignite new star formation in a sweeping ring. In other words, the strange beauty is the frozen aftermath of a cosmic strike. The dramatic part is not just the shape, but the timescale. The ring we see marks an event that unfolded over immense stretches of time, yet the pattern still reads as a single blow. It is like watching a splash spread across a pond, except the pond is a galaxy, and the ripples are measured in light years. Strange galaxies often tell stories. This one almost shows the impact frame by frame. Some galaxies wear glowing rings of newborn stars around empty centers. At first glance, those rings can feel decorative, as though the galaxy has lit itself for display. The reality is more dynamic. A bright ring usually marks a region where gas has been compressed strongly enough to collapse into fresh stars. The center can look subdued by comparison, either because its active period has passed or because material has been cleared, shifted, or prevented from gathering there. In some galaxies, a bar-shaped structure channels gas inward and piles it up at a certain distance, creating a star-forming ring. In others, an encounter or impact sets the pattern. What makes these systems so captivating is the contrast between emptiness and activity. Instead of spreading evenly, the galaxy places its brightest youth in a circle, like a band of fire around a calmer middle. That strange arrangement reveals that star formation is not always a general glow. Sometimes it happens in chosen lanes, as if the galaxy has found one narrow place where creation still thrives. Polar ring galaxies carry a second galaxy's debris, like a halo. These are among the most startling objects in the sky, because they seem to disobey the usual arrangement of a galaxy. There is a main body, often broad and smooth, and then there is a second ring of stars, gas and dust orbiting almost at right angles around it. It can look like one galaxy wearing another one. The most likely explanation is theft. Material from a passing or captured companion was pulled away and settled into a strange orbit that remained stable long enough to become a lasting structure. That makes each polar ring a visible record of acquisition. It also makes these galaxies useful because the odd geometry helps astronomers study how mass is distributed, including the unseen dark matter halo surrounding the system. The appeal is immediate even before the science begins. A normal galaxy feels like one world. A polar ring galaxy feels like two systems crossing through each other, suspended in a balance that seems too unlikely to be real. The Sombrero Galaxy hides a giant bulge inside a razor-thin disk. From Earth, it looks dignified and strange at the same time. A bright central bulge swells upward like the crown of a hat, while a narrow, dark lane cuts across the middle and marks the flat disk. The nickname is irresistible, but the structure behind it is even better. The central region is unusually large and densely packed with older stars, giving the galaxy a powerful glow at its heart. Around that sits a thin disk rich in dust, which blocks light and sharpens the contrast so beautifully that the whole object seems almost sculpted. It is fascinating because it appears halfway between familiar categories. Part spiral, part something more massive and smooth. It refuses to fit too neatly. Seen from the right angle, its geometry becomes almost theatrical. Yet every line in that profile comes from real material, real motion, and real history. This is a galaxy that teaches how much character can depend on structure, dust, and the luck of our viewpoint. Needle galaxies look impossibly thin because we see them edge on. A spiral galaxy seen face-on can display graceful arms and broad curves. Turn that same system sideways, and the view changes completely. The disk compresses into a slender streak of light so narrow that it can look unreal, almost like a scratch across the darkness. That is why some are called needle galaxies. Their apparent thinness is partly a trick of orientation, but it is also a reminder of how flat many galactic disks really are compared with their enormous width. In edge-on views, dust lanes become especially striking because they slice through the glow like dark seams. Bulges stand out more clearly too, rising above the line of the disk. These galaxies are wonderful for the imagination because they reveal form through silhouette. They let us see a galaxy not as a pinwheel, but as a layered structure with depth, thickness, and internal architecture. A small change in angle turns something familiar into something so sharp and strange that it feels newly discovered. The Black Eye galaxy bears a dark bruise of dust. What makes this galaxy so memorable is the impression of injury. One side of the bright central region is partly covered by a thick, dark band of dust, giving the object an appearance that really does resemble a bruised eye. The effect is dramatic, but it also carries information. Dust lanes like this are made of tiny grains mixed with gas, and they can block starlight so effectively that parts of a galaxy seem cut away. In this case, the uneven structure suggests a disturbed past. Astronomers think the galaxy may have interacted with a smaller companion, leaving behind a mismatch between different components of the system. There is evidence that material inside may not all be moving in the same simple pattern, which deepens the sense that something happened here. The fascination comes from how personal it looks. A galaxy is an unimaginably vast system, yet this one seems marked by a visible wound. It turns a remote object into something almost emotionally legible. The Cigar Galaxy is bursting with stars and violent winds. Messier 82 looks narrow and compressed from our viewpoint, but its real drama lies in the turmoil inside. This galaxy is undergoing an intense starburst, which means it is forming new stars at a rate far above normal. That kind of activity does not stay quiet. Massive young stars shine fiercely, live briefly, and explode as supernova, dumping energy into the surrounding gas. The combined force drives enormous outflows above and below the disk. In images, those plumes can appear as red streams and filaments reaching into space, as though the galaxy is venting its own interior. The likely trigger was a gravitational interaction with its larger neighbor, Messier 81, which disturbed gas and helped ignite this frenzy. What makes it so gripping is that it feels alive with consequences. The same event that creates brilliant new stars can also blow material away and change the galaxy's future. Creation and disruption are happening together in one compressed, spectacular system. Centaurus looks misshapen because it swallowed another galaxy. This is the kind of object that tells its story right on the surface. The overall body looks like a large, smooth galaxy, yet a thick, dark lane cuts across it in a way that feels completely out of place. That lane is packed with dust and gas, and it almost certainly came from a smaller spiral galaxy that was torn apart and absorbed. Rather than blending instantly, the captured material remained as a striking band that still gives the system its peculiar appearance. Centaurus A is fascinating for another reason too. Its central black hole is actively feeding, and the galaxy is a powerful source of radio emission, with vast jets extending far beyond the visible body. So this is not just a merger remnant. It is also one of the great active galaxies in the nearby universe. You can almost read two stories at once, one of consumption and one of ignition. It looks wounded, fed, altered, and energized, all at the same time. The tadpole galaxy trails a tail of stars behind it. Its nickname comes from one of the most dramatic features any galaxy can display: a long, luminous tail stretching outward as though the whole system is swimming through space. That tail was not drawn out by motion through empty darkness. It was created by gravity during a close encounter with another galaxy. As the two systems interacted, stars and gas were pulled outward into an extended stream. Within that tail, bright blue star clusters formed, adding sparkle to what might otherwise have been only a scar. This is one of the reasons tidal tails are so captivating. They're not just debris. They can become places where new structure appears. The tadpole galaxy makes galactic interaction feel immediate because the evidence is so visible and so elegant. You do not need a diagram to understand that something powerful happened here. One glance tells you that gravity reached into a whole galaxy, grabbed hold of its outer regions, and drew part of its history out into the open. Some galaxies have no graceful spiral arms at all. When people picture a galaxy, they often imagine the clean sweep of a spiral. That image is famous for a reason, but it is far from universal. Many galaxies do not show those elegant arms, and some never did. Instead, they may look smooth, lumpy, boxy, or simply undefined, with stars spread in forms that feel less decorative and more bluntly physical. That absence matters because spiral arms are not just ornaments. They are connected to motion, density patterns, and the way gas and stars are organized across a disk. Without them, a galaxy tells a different story about how it formed, how it evolved, and what forces shaped it. Some may have lost ordered structure through collisions. Others may be too small or too poor in gas to support it. The fascination lies in the contrast with expectation. Once you realize galaxies do not owe us symmetry or grace, the universe becomes much richer. Even a galaxy without grand curves can be full of clues. Irregular galaxies look chaotic because gravity has pulled them apart. These galaxies often seem to ignore every neat category. They may lack a central bulge, a defined disk, or any obvious symmetry. Instead, you see scattered bright regions, uneven clumps, and shapes that feel unfinished or disturbed. That appearance is often the result of interaction. Gravity from a nearby companion can tug, compress, and distort a smaller galaxy until ordered structure gives way to something rougher and more fragmented. The large and small Magellanic Clouds, which orbit near the Milky Way, are famous examples of irregular galaxies shaped by complex relationships with each other and with our own galaxy. They remind us that chaos in astronomy is often relational. A galaxy may look misshapen not because it failed to form properly, but because it has been living in company. That is part of what makes irregular galaxies so compelling. They feel less like settled islands and more like ongoing events. Their asymmetry is not emptiness of design. It is evidence that gravity has kept working on them. Dwarf galaxies can be tiny, yet still reshape larger neighbors. It is tempting to think only giants matter in galactic history, but dwarf galaxies can be surprisingly influential. These small systems contain far fewer stars than major spirals or ellipticals, yet they often serve as the raw material from which bigger galaxies grow. When a dwarf falls toward a larger system, gravity can tear it apart and spread its stars into long streams. Those streams do not simply vanish. They add mass, alter motion, and leave behind signatures that astronomers can still detect. Repeated over cosmic time, such events help build halos, thicken disks, and reshape the outskirts of great galaxies. The remarkable part is the mismatch in scale. A system that might seem minor on its own can leave traces across enormous distances once it is stretched and absorbed. Dwarf galaxies are fascinating because they show that importance in the universe is not always tied to size. Sometimes the smaller partner becomes unforgettable precisely because it is consumed. A small galaxy can feed a much larger one for ages. When a dwarf companion begins to fall into a giant galaxy, the process is rarely quick. Gravity strips material gradually, peeling away stars, gas, and dark matter over repeated passes. With each orbit, more of the smaller system is removed and added to the larger one. That means feeding can happen in stages, almost like a long, slow transfer rather than a single dramatic event. The Sagittarius dwarf galaxy offers a vivid example near the Milky Way. It is being torn apart even now, and its stars are spread into streams that wrap around our galaxy. These are not merely leftovers. They are active evidence that growth can happen by steady accretion. The larger galaxy gains mass and structure, while the smaller one is transformed into a pattern stretched across the sky. What makes this so gripping is the patience of it. A galaxy can be eating for vast spans of time, and the meal itself becomes part of the visible architecture of the eater. Some galaxies are so diffuse they are almost ghostly. Not every galaxy announces itself with bright arms or a glowing core. Some are spread so thinly that their stars are scattered across a wide region with very little concentrated light. Against the blackness of space, they can look like faint smudges that are barely there at all. Yet these systems are real galaxies, not failed observations. They contain stars, mass, and histories, but their light is diluted over such large areas that they are easy to miss. That ghostly quality makes them deeply appealing. They challenge the idea that a galaxy must be obvious to be important. In many cases, these faint systems survive in environments where stronger interactions might have torn denser galaxies into more dramatic forms. Their existence also warns astronomers that the universe may contain more structure than bright surveys first revealed. Some galaxies do not dominate the sky. They haunt it. You notice them only when your eyes and instruments become sensitive enough to catch what almost disappears. Ultra-diffuse galaxies spread their stars across enormous empty volumes. These galaxies can be as large as the Milky Way in overall size, yet contain only a tiny fraction of its stars. That combination is what makes them so astonishing. Imagine taking a substantial galaxy and thinning it until the starlight is spread over such a vast area that the whole thing becomes faint and fragile-looking. Some ultra-diffuse galaxies live in crowded galaxy clusters, which makes their survival even more puzzling. In such busy regions, gravity is rough, and delicate systems might be expected to fall apart. Yet they persist. Astronomers are still working out how they formed. Some may have lost gas early and failed to build many stars. Others may sit inside unusually massive dark matter halos that help hold them together despite their sparse appearance. The fascination comes from scale mismatch. They look almost empty, but they occupy enormous space. They feel like galaxies stretched toward transparency, as though the universe experimented with how little light it could use and still make a galaxy. Dark galaxies may hold gas and mass, yet almost no stars. This is one of the strangest ideas in astronomy because it challenges the very way we notice galaxies. Usually a galaxy is discovered because its stars shine. A dark galaxy would be different. It would be a system rich in gas and mass, perhaps wrapped in dark matter, but with little or no star formation to make it obvious in visible light. In principle, such an object could exist as a gravitational structure, but mostly escapes ordinary notice. Astronomers search for candidates by looking for clouds of hydrogen, unusual motions, or effects on nearby visible galaxies. The reason this is so compelling is that it suggests the universe may build galactic frameworks without always lighting them up. A galaxy could be there in a structural sense, yet remain nearly invisible because the usual beacon of stars never properly ignited. That possibility makes the cosmos feel more secretive. It hints that some of its architecture may be present long before, or even without, the luminous display we expect. Some galaxies are visible mostly because their gas glows. Starlight is not the only thing that can make a galaxy stand out. In certain cases, glowing gas becomes the most striking feature. Gas can shine when it is heated, ionized by intense radiation, or stirred by energetic processes such as shock waves, star formation, or activity near a central black hole. Under those conditions, clouds of hydrogen and other elements emit light in distinctive colors that telescopes can capture beautifully. This can reveal filaments, loops, and broad patches that seem to hang around the galaxy like luminous weather. What makes that so fascinating is the shift in emphasis. Instead of seeing a galaxy mainly as a population of stars, you begin to see it as an environment of active material, moving, reacting, and broadcasting its physical state. The glow becomes a map of energy at work. In some strange galaxies, that glowing gas is what first tells astronomers something dramatic is underway. It is the visible breath of processes that might otherwise remain hidden. A galaxy can be real, massive, and still nearly invisible. This sounds like a contradiction, yet astronomy is full of such surprises. Visibility depends on how light is concentrated, what kind of light is produced, and whether our instruments are tuned to detect it. A galaxy with few stars, very spread out stars, or stars buried behind dust can be easy to overlook even if it contains substantial mass. On top of that, most of a galaxy's matter may not shine at all if dark matter makes up the dominant share. That means there can be a deep difference between what looks important and what actually is important dynamically. This is part of why strange galaxies matter so much. They teach us not to trust brightness alone. A faint object can still bend, tug, influence, and persist. The universe is not arranged according to what is most visible to human eyes. Sometimes a galaxy's power lies in what does not announce itself. The discovery of such systems expands not only our maps, but our intuition about what counts as presence. Low surface brightness galaxies can hide in plain cosmic sight. These galaxies are not necessarily tiny or distant. The problem is that their light is spread so thinly across the sky that they blend into the background. Surface brightness measures how much light comes from a given area, and when that value is low, even a large galaxy can become difficult to notice. It may sit in images for years without standing out, especially if brighter objects draw the eye away. That is what makes them so intriguing. They are not hidden behind some exotic curtain. They are hidden by understatement. Once found, they open a different window on galactic life. Many are rich in gas and dark matter, with relatively modest star formation. Some seem to have evolved slowly, avoiding the dramatic bursts or dense structures seen elsewhere. They can feel like the quiet underclass of the galactic world, present all along, yet easily ignored. Discovering them is a reminder that the sky still contains secrets, not because they are impossibly far away, but because they shine too softly to demand attention. Ring galaxies may form when one galaxy punches through another. There are few better examples of cosmic violence leaving behind elegance. When a smaller galaxy plunges through the disk of a larger one, the encounter can send a density wave racing outward, rather like a ripple spreading across water after a stone strikes the surface. But here, the surface is a galaxy full of gas, dust, and stars. As that wave moves through the disk, it compresses gas and can trigger fresh star formation in a growing circle. The result is a bright ring that marks the path of disturbance long after the intruder has passed. What makes this so gripping is the clarity of the geometry. A chaotic event can leave behind a shape so simple, but it feels deliberate. The ring is not decoration. It is impact made visible. In these galaxies, gravity behaves like a sculptor with terrible force, and one brief crossing can reorganize the visible structure of an entire stellar system. Colliding galaxies do not usually crash, star into star. This is one of those facts that feels wrong until you picture the scale properly. Galaxies look crowded in photographs because countless stars are packed into a luminous pattern. In reality, the distances between stars are enormous. Even when two galaxies pass through each other, the odds of one star directly striking another are extremely low. What really collides is the larger structure. Gravity distorts both systems. Gas clouds can slam together, compress, and ignite star formation. Orbits are altered. Shapes are stretched. Tails, bridges, and warped disks begin to appear. So a galactic collision is not a chaotic pileup of suns. It is more like two vast swarms passing through each other, while their shared gravity rearranges everything. That contrast is part of what makes these events so fascinating. They are violent without being crowded in the way we instinctively imagine. The damage happens through influence, momentum, and pressure, not through countless direct impacts between stars. Galactic mergers are slow, graceful disasters that can last eons. A merger is not one event. It is a sequence of meetings, separations, returns, and final surrender. Two galaxies may first brush past each other and keep going, only to be pulled back together by gravity over immense spans of time. With each pass, they lose energy, disturb each other's structure, and draw closer to a final union. Stars are redistributed. Gas is driven inward. Dark halos overlap and combine. Seen in snapshots across the universe, mergers can look like a gallery of stages in one enormous process. Some pairs remain distinct but distorted. Others seem half-blended, with multiple bright cores still visible. In the end, the original identities may be almost impossible to recover. What makes this beautiful is the slowness. The forms produced by mergers can be dramatic, yet every curve and plume records an interaction unfolding with majestic patience. It is destruction, but not in a sudden burst. It is a long reshaping, carried out by gravity over unimaginable time. Some galaxies grow long tidal tails during close gravitational encounters. A close pass between galaxies can pull matter outward with extraordinary reach. Instead of remaining in neat disks or settled halos, stars and gas are drawn into elongated streams called tidal tails. These tails can stretch across immense distances, glowing faintly as evidence that gravity has reached into a galaxy and dragged part of it away. The effect can be spectacular because it turns motion into visible calligraphy. One side may extend far into space, while the main body remains behind, distorted but still intact. Sometimes both galaxies produce tails, which gives the whole system an appearance of unraveling. These structures are more than scars. They preserve information about the masses involved, the angle of approach, and the strength of the encounter. In some cases, they even host new star clusters formed from material torn loose in the interaction. That is part of their magic. A tail looks like loss, yet within it you can sometimes see fresh creation beginning in the wake of disruption. Bridges of stars can stretch between galaxies in mid-Chalcyon. Tails are what matter flung outward looks like. Bridges are what matter caught between looks like. During a close interaction, Gravity can draw streams of stars and gas into the space connecting two galaxies, making them appear linked by a luminous thread. It is one of the most striking sights in astronomy, because the bridge turns an invisible force into something almost tangible. You can look at it and feel the pull between the two systems. These structures often form while the galaxies are still distinct, which gives the impression that they are being slowly stitched together before the final merger. Gas within the bridge may collapse into new star-forming knots, adding bright patches to the connection. That makes the region between galaxies feel active rather than empty. A bridge is fascinating because it shows that a collision is not only about damage to each individual system. It is also about the temporary architectures that arise between them, as gravity rewrites where matter belongs. A merger can scramble a spiral galaxy into an ellipse. Spiral galaxies are known for ordered disks and elegant arms, but those structures can be fragile when a major merger occurs. If two substantial galaxies combine, the repeated gravitational turmoil can disrupt the rotating disk that once kept stars in a flattened arrangement. Instead of continuing in one tidy plane, stellar orbits are scattered into many directions. Over time, the result can become a smoother, rounder, more three-dimensional system that we classify as an elliptical galaxy. This is one of the great transformations in cosmic evolution. A form that seems graceful and stable can be turned into something very different through interaction. The fascinating part is that the aftermath may look calm. An elliptical galaxy often appears settled and featureless compared with a spiral. Yet that smoothness can be the final state of profound upheaval. Hidden beneath the simple outline is a history of collisions, mixing, and lost structure. Sometimes the quietest-looking galaxy is what remains after a long period of cosmic wreckage. Collisions can wake sleeping gas and ignite furious starbirth. Gas inside a galaxy can spend long periods drifting without forming many stars. Then, an interaction changes everything. When galaxies pass near each other or begin to merge, gravity can compress gas clouds, disturb their motion, and drive material into denser regions. Once enough gas is squeezed together, collapse begins and star formation surges. A system that seemed modest can suddenly blaze with young, hot stars. This is one reason galactic collisions are so important. They do not only tear structures apart, they can also trigger one of the most productive phases in a galaxy's life. The contrast is wonderful. A disruptive encounter becomes the very thing that starts a creative outburst. Massive blue stars light up the disturbed regions, and clusters can form in numbers far above the usual pace. In some galaxies, the brightest evidence of a past collision is not a scar, but a bloom. The chaos awakens material that had been waiting, and the result is a burst of new light. Two galaxies can dance for ages before finally becoming one. There is a reason astronomers often speak of dancing. When two galaxies become gravitationally bound, they do not always merge straight away. They may circle one another, draw close, separate, and return again, each passage altering their shapes and motions. Seen over enough time, the interaction resembles a drawn-out choreography in which every approach changes the next step. Tidal arms lengthen, cores brighten, gas shifts inward. The pair may look tender from a distance, almost like two luminous forms leaning together, yet the process is entirely governed by gravity. What makes this image so powerful is the combination of beauty and inevitability. Once enough energy has been lost through the interaction, the dance has only one ending. The galaxies will eventually coalesce into a single system. Until then, the universe gives us these extraordinary intermediate stages, where two great stellar islands are neither separate nor united, but caught in a long mutual surrender across the dark. Some strange galaxies are snapshots from the middle of a wreck. Astronomy has one great advantage over storytelling. The universe provides countless examples of the same process at different stages, so we can piece together long events from scattered moments. A disturbed galaxy may show a twisted disk, a double core, a stretched tail, or a bridge to a companion. Each feature tells us we are seeing not a final form, but a system caught in transition. It is like finding a photograph taken halfway through a collapse, a merger, or an upheaval, and having to infer what happened before and what comes next. That is part of the thrill. Strange galaxies are often not separate classes of object so much as dramatic moments in evolution. They are temporary forms that happen when a galaxy is being remade. The universe is full of these interrupted states, and they reveal that structure is not fixed. A galaxy can spend millions of years looking unlike itself, suspended between one identity and another, while the wreck is still unfolding. Galactic cannibalism is one of the universe's favorite building methods. The phrase sounds brutal, but it captures something fundamental. Large galaxies often grow by absorbing smaller ones. A dwarf companion falls in, begins to lose stars and gas, and is gradually dismantled by tidal forces. Over time, its material becomes part of the larger galaxy's halo, disk, or central regions. This is not a rare accident. It appears to be one of the standard ways galaxies assemble over cosmic history. Even giant systems in clusters can consume neighbors and continue building themselves through repeated accretion. The fascinating part is that a galaxy can become grand, not by staying untouched, but by feeding on others, again and again. Growth is cumulative and often messy. Streams, shells, and kinematic oddities can all remain as evidence of what was eaten. That means every large galaxy may be, in part, a collection of older victims preserved within a newer whole. Their beauty is not pure inheritance. It is built from capture, breakdown, and incorporation over time. Starburst galaxies can form stars at astonishingly frantic rates. Most galaxies make stars at a pace that, while impressive by human standards, is relatively modest on cosmic ones. A starburst galaxy is different. For a limited period, it can produce new stars many times faster than usual, as if some long-restrained reservoir of gas has suddenly been set loose. This can happen after interactions, mergers, or internal instabilities drive material into dense regions where collapse becomes unavoidable. The result is a galaxy that briefly behaves like a stellar factory in overdrive. Massive young stars appear in great numbers, bathing their surroundings in intense radiation and reshaping the gas around them. What makes this so compelling is the sense of urgency. A starburst is not a calm, long-term mode of life. It is a rush, a phase of almost reckless productivity that cannot last forever. In these galaxies, you are seeing creation accelerated to a dramatic extreme, with all the brilliance and all the future consequences packed into one short, luminous episode. Some galaxies burn through their gas in brief, brilliant outbursts. A galaxy's gas supply is the raw material for future stars, so using it quickly carries a cost. In certain systems, star formation becomes so intense that the available gas is consumed far faster than normal. Instead of sustaining a slow, steady pace over long ages, the galaxy enters a brief but dazzling phase of overuse. That outburst can be triggered by a merger or another event that drives gas inward and compresses it beyond the usual conditions. For a while, the galaxy shines with the energy of fresh stars, supernova, and active regions. But the brilliance contains its own ending. Once enough gas has been turned into stars or blown away by stellar feedback, the frenzy fades. What makes this so fascinating is the sense of a galaxy living beyond its means. It is not simply bright. It is spending its future to create a dramatic present. The glow becomes more poignant when you realize it may be the light of a system exhausting its best fuel. A starburst can make a galaxy blaze in infrared light. Young stars are brilliant, but in many starburst galaxies, their light does not travel outward cleanly. Thick dust absorbs much of the visible radiation and warms up in the process. That heated dust then re-radiates the energy at infrared wavelengths, which means a galaxy that might look modest in ordinary light can be blazing furiously in the infrared. This changed astronomy in a profound way because it revealed a hidden population of intensely active galaxies that were easy to underestimate or even overlook. Infrared observations showed that dust is not merely an obscuring nuisance. It can be the key to finding where the real action is. In the starburst system, the brightest story may be written not in starlight we can see with our eyes, but in thermal glow coming from dust loaded with absorbed energy. That makes the galaxy feel almost double-layered, dim in one sense and overwhelming in another, with its true power emerging only when we look in the right way. Strange galaxies often glow brightest where dust hides the action. At first, that seems unfair. Dust sounds like the thing that should block understanding, not sharpen it. Yet in many unusual galaxies, the most energetic regions are wrapped in so much dust that visible light alone gives a misleadingly calm picture. Dense clouds absorb and scatter the radiation from newborn stars or active central regions, concealing the true intensity within. But that same dust heats up and glows at longer wavelengths, allowing astronomers to uncover the hidden drama with infrared and radio observations. This creates one of the most intriguing reversals in astronomy. The very material that hides the action also signals it. A dust-rich galaxy can look dark or patchy in one image, then erupt with brightness in another. That is part of what makes strange galaxies so rewarding. They teach us not to trust first appearances. A region that seems muted may be the site of extraordinary violence or creation, wrapped in a veil that only changes what kind of light escapes. Dust can conceal billions of young stars from ordinary telescopes. A newborn star-forming region can be crowded with fresh, luminous stars, yet still remain hard to see in visible light if dust is thick enough. Tiny grains mixed through the gas absorb and redden the light, sometimes almost completely blocking the view. In galaxies undergoing intense star formation, those dusty regions can be vast. That means enormous populations of young stars may be present, while optical images show only fragments of the truth. This is one of the reasons astronomers rely on multiple wavelengths. Infrared light can penetrate dust more effectively, revealing activity that would otherwise be hidden. The idea is astonishing when you stop and picture it. A galaxy may contain billions of hot young stars, and an ordinary image can still fail to show where most of them are. The universe can hide abundance behind fine material scattered through space. Dust does not need to be massive to be influential. A thin veil, spread widely enough, can keep a whole generation of stars partially out of sight. Infrared astronomy revealed galaxies that looked calm but were raging. Before infrared observations became powerful enough to transform the field, some galaxies seemed unremarkable in visible light. They appeared dusty, subdued, or only moderately active. Then astronomers looked at longer wavelengths and found something astonishing. Beneath that muted appearance, some of these systems were pouring out enormous amounts of energy. Hidden starbursts and buried active nuclei were lighting up the dust so strongly that the galaxies became luminous giants in the infrared. This was a reminder that visible light shows only part of the story. A galaxy can wear a calm face while enormous processes unfold behind the veil. That discovery changed not just individual classifications, but the whole sense of what the universe might be hiding. It taught astronomers to search for power in places that did not look dramatic at first glance. The fascination lies in the reversal. A galaxy once dismissed as ordinary can turn out to be one of the most energetic objects in its region, revealed only when we learn to see beyond the obvious. Some galaxies launch superwinds powered by exploding newborn stars. In a galaxy with intense star formation, the youngest massive stars live fast and die violently. Their radiation, stellar winds, and supernova explosions dump staggering amounts of energy into the surrounding gas. When enough of that energy accumulates in a concentrated region, it can drive material outward in a large-scale outflow known as a superwind. These winds can rise above and below the galactic disk like vast plumes, carrying hot gas, heavier elements, and traces of the starburst into intergalactic space. This is one of the most dramatic ways a galaxy can influence its surroundings. It does not merely form stars. It breathes matter outward on colossal scales. What makes superwinds so fascinating is their dual nature. They are born from creation, yet they act like evacuation. The very process of making stars can start pushing material away from the place where future stars might have formed. A galaxy in starburst can become not only a cradle, but also a source of powerful expulsion. Those winds can blow gas completely out of a galaxy. When a galaxy drives a strong enough outflow, the escaping gas may not all fall back. In smaller galaxies especially, the pull of gravity can be weak enough that superwinds carry material beyond the system for good. That matters enormously, because gas lost to space is gas that can no longer form future generations of stars. The galaxy is not merely venting heat or rearranging clouds. It may be permanently reducing its own ability to keep building itself. This gives starburst activity a kind of self-destructive edge. The same burst of creation that fills a galaxy with youthful light can also launch the material needed for later creation out into the dark. It is a powerful example of feedback, where one process limits the next. The image is striking too. You can imagine a galaxy flaring into life so intensely that it begins to empty itself. In that sense, some of the brightest periods in a galaxy's history are also moments of real cosmic loss. A galaxy can trigger its own future silence by making stars too fast. There is a paradox at the heart of starbursts. The more efficiently a galaxy turns gas into stars, the more quickly it risks ending the conditions that made the burst possible. Gas can be consumed directly, heated so it resists collapse, or expelled by winds and supernova-driven feedback. Over time, the furious pace of creation undermines the raw material for future creation. That means a galaxy's brightest episode may also be the beginning of a quieter era. Astronomers see evidence that some systems shut down star formation after intense active phases, leaving behind older stellar populations and much less cold gas. This is fascinating because it makes a galaxy feel almost tragically dramatic. It shines with extraordinary energy, yet hidden inside that brilliance is the seed of its own decline. The universe often works that way. Extremes are hard to sustain. In these galaxies, you can watch abundance becoming exhaustion. A dazzling peak in activity can be the very thing that prepares a long fading afterward. Strange galaxies often live between creation and exhaustion. Many of the most compelling galaxies are caught in an unstable middle state. They are neither calm star factories with a long future ahead, nor fully spent systems resting in old age. Instead, they seem to occupy a threshold. Gas is still present, but under pressure. New stars are forming, but so are the winds and feedback processes that may halt future growth. Mergers may be stirring fresh activity even as they scramble older structure. This in-between condition is part of why strange galaxies feel so alive. They are not static categories. They are places where opposing tendencies meet. Building and depletion, ignition and shutdown, brightness and loss can all be visible at once. That tension makes them deeply engaging to study and to imagine. A galaxy in such a phase is telling a story with no settled ending yet. It has not become what it will be, but it cannot remain what it was. We are seeing it during the costly, luminous act of becoming. Active galaxies are powered by black holes that are feeding. At the heart of many galaxies sits a supermassive black hole, but only some become dramatically active. The difference is food. When enough gas and dust fall inward, they do not drop straight through the event horizon at once. Instead, they whirl into a tight disk, collide, heat up, and release astonishing amounts of energy before disappearing. That process can outshine the surrounding galaxy and turn the center into one of the brightest engines in the universe. The black hole itself remains dark, yet the material on its way in becomes a beacon. This is what makes active galaxies so thrilling. A region smaller than the galaxy by a vast margin can dominate the whole system's appearance and behavior. You are seeing gravity doing work with extraordinary efficiency. Not through burning fuel in the ordinary sense, but through the release of energy as matter falls deeper into a gravitational well. It is feeding that makes the darkness seem almost impossibly bright. A feeding black hole can turn a galaxy's core into a beacon. Picture a whole galaxy full of stars, then imagine one tiny central region becoming so luminous that it steals the scene. That is what happens when matter is funneled toward a supermassive black hole in sufficient quantity. The gas forms an accretion disk, and friction within that disk drives temperatures so high that it radiates across the spectrum. Ultraviolet light, visible light, X-rays and more can pour outward from a place that, on galactic scales, is astonishingly small. This is why active galactic nuclei feel so dramatic. They take the familiar idea of a galactic center and transform it into a blazing powerhouse. In some cases, the surrounding stars become visually secondary. The fascination lies in the imbalance. Billions of suns spread across a galaxy may be present, yet a compact region around one black hole becomes the dominant source of light. The core stops being a quiet anchor and becomes the loudest part of the whole system. Quasars are galaxies whose centers shine brighter than everything else. When quasars were first discovered, they seemed almost absurd. They looked like point-like sources, almost star-like, yet their redshifts showed they were astonishingly distant. If they were that far away and still so bright, then their power had to be immense. The answer was that these were not ordinary stars at all, but galaxies with unbelievably active central engines. Their outer stars were present, but the nucleus was so luminous that it overwhelmed the rest. A quasar is what happens when a supermassive black hole is fed on a grand scale. Matter spirals inward, heats intensely, and pours out radiation that can cross the observable universe. What makes quasars so captivating is the sense of concentration. An entire galaxy may be involved, yet the most dramatic light comes from a small central region. They remind us that the brightest things in the cosmos are not always the biggest structures. Sometimes they are the fiercest hearts inside them. Some quasars are visible across most of the known universe. That alone is enough to make them feel almost mythical. Light from certain quasars began its journey when the universe was far younger than it is now. Yet those objects still shine strongly enough for modern telescopes to detect them across billions of light years. This means we are not only seeing extreme brightness. We are seeing ancient activity preserved in light that has traveled for most of cosmic history. A quasar is powerful enough to remain noticeable over distances that reduce whole galaxies to faint whispers. That is why they matter so much to astronomy. They become beacons from deep time, allowing researchers to probe the early universe, the growth of black holes, and the state of intergalactic matter along the line of sight. The emotional impact is just as strong as the scientific one. To look at one of these objects is to receive a signal sent from an age when the cosmos was young, by a galaxy whose central engine was bright enough to survive the journey to us. Blazars look extreme because their jets point toward us. Some active galaxies produce narrowed jets of particles and radiation launched from the region around the central black hole. When one of those jets happens to be aimed almost directly at Earth, the galaxy can appear extraordinarily bright and erratic. That is what defines a blazar. The object is not necessarily unique in its basic machinery. What changes the experience is our angle. Because the jet is pointed toward us, its emission is boosted and intensified, making the galaxy seem far more violent and variable than it might from another viewpoint. This is a wonderful reminder that strangeness in astronomy is sometimes a matter of perspective. Orientation can transform a distant galaxy into one of the most dramatic sights in the sky. Blazars flash, flare, and pour out energy across the spectrum, from radio waves to gamma rays. They feel like cosmic searchlights, not because they are sweeping the universe at random, but because by chance one of their narrow beams is aimed our way. Radio galaxies fire colossal jets far beyond their visible stars. In visible light, a radio galaxy may look impressive but contained, like any large galaxy with a bright center. Then radio observations reveal something far larger and more astonishing. Huge jets are blasting outward from the central region, carrying energy far beyond the body of the galaxy itself. At their ends, giant lobes can form where the jets interact with surrounding matter, creating structures that dwarf the visible starlight. This is one of the great shocks of multi-wavelength astronomy. The familiar galaxy becomes only the core of a much bigger system shaped by invisible power. What makes radio galaxies so memorable is scale. The black hole at the center is tiny compared with the galaxy, yet it drives outflows that can dominate regions vastly larger than the stars we first notice. A normal-looking galaxy suddenly reveals itself as the anchor point of an enormous energetic machine. The visible part is only the beginning. The true drama is unfolding in radio space far beyond it. A black hole jet can stretch longer than the galaxy itself. It sounds exaggerated until you see the observations. Jets launched from the vicinity of a supermassive black hole can remain focused over extraordinary distances, crossing beyond the visible body of the host galaxy and continuing for lengths that make the galaxy seem almost small by comparison. This is one of the most astonishing examples of concentrated power in nature. A central engine occupying a tiny fraction of the galaxy can produce structures that reach into the surrounding environment on immense scales. The physics behind those jets is still an area of deep study, involving magnetic fields, rotation, and the violent conditions near the black hole. But even without the equations, the visual fact is enough to stir wonder. A galaxy is already a vast thing. For a jet to exceed it in length feels like seeing the influence of the center escape all reasonable proportion. It turns the black hole from a local feature into a cosmic projector, throwing energy outward in long, disciplined lines. Some galactic cores flicker because matter falls in unevenly. An active galactic nucleus is not always steady. In some cases, the brightness rises and falls over time, sometimes surprisingly quickly. That variability is one of the clues that the source is compact. If a whole galaxy were brightening and dimming together, the changes would be smoothed out over vast scales. But a small central region can fluctuate when the flow of matter into the black hole changes, when instabilities ripple through the accretion disk, or when the geometry of the emitting region shifts. This makes active cores feel less like lamps and more like weather systems, unsettled and alive with changing conditions. The fascination lies in the immediacy. A galaxy may seem eternal and slow, yet its heart can flicker on humanly meaningful timescales of days, months, or years. That contrast is thrilling. Hidden inside an ancient system of stars is a restless engine whose light betrays the uneven rhythm of matter as it spirals toward the point of no return. A strange galaxy can roar in radio waves and whisper in visible light. Not all galactic drama announces itself where human eyes would notice it. Some galaxies appear fairly modest in visible light, perhaps only a calm stellar body with a dusty center. Yet at radio wavelengths they become extraordinary, with jets, lobes, and energetic structures revealing a level of activity that optical images barely suggest. This is one of the most powerful lessons in modern astronomy. The universe does not owe its most important truths to the narrow band of light our eyes can see. A galaxy can seem restrained in one view and thunderous in another. Radio observations uncover electrons spiraling in magnetic fields, exposing processes tied to black hole jets and large-scale outflows. What makes this so compelling is the mismatch between appearance and reality. The galaxy whispers one story in starlight and shouts another in radio emission. To understand strange galaxies, astronomers must learn to listen in many languages of light, because the loudest one is not always the most familiar. The brightest galactic monsters are powered by gravity, not fire. When we think of immense brightness, we often think of burning. Stars shine because nuclear fusion releases energy in their cores. But the most luminous galactic centers do not need that mechanism. Their power comes from matter falling inward under gravity. As gas descends toward a supermassive black hole, it loses gravitational energy, and that loss can be converted into radiation with astonishing efficiency. In some regimes, accretion can outperform fusion in the amount of energy released per unit of matter. That is one reason active galactic nuclei can become so brilliant. They are not giant fires in the ordinary sense. They are gravity engines. This idea is part of what makes them feel so strange and profound. The same force that holds galaxies together can, under the right conditions, create some of the brightest sustained emission in the universe. The black hole is not shining by itself, but the path toward it becomes a furnace of light. The monster glows because matter is falling. Ciphered galaxies look ordinary until their cores reveal unusual fury. A ciphered galaxy can be wonderfully deceptive. At first glance, it may resemble a familiar spiral or another fairly normal galactic form, with stars spread in a recognizable structure and no obvious sign of extremes. Then the core gives itself away. Bright emission, unusual spectra, and energetic radiation reveal that the central region is active and far more intense than the overall appearance suggests. These galaxies are captivating because they bridge the gap between the normal and the extreme. They are not as overpowering as the brightest quasars, yet they show the same basic phenomenon of a feeding central black hole. That makes them feel close enough to grasp. The host galaxy still looks like a place where stars live in large-scale order, but at its heart, something restless and powerful is underway. Ciphered galaxies remind us that the difference between ordinary and extraordinary can be concentrated in a small, central zone. A galaxy does not need to look bizarre overall to hide a dramatic engine. Some galactic nuclei are hidden behind thick walls of dust. A supermassive black hole can be actively feeding while remaining concealed from direct optical view. Around some galactic centers, dense, dusty material forms a shrouding structure that blocks much of the visible light from the nucleus, depending on the angle from which we observe the galaxy. That means two galaxies with similar central engines can appear very different, simply because one gives us a clearer line of sight and the other does not. This idea is part of the unification picture of active galaxies, and it is deeply satisfying because it turns mystery into geometry. The nucleus is not absent. It is obscured. What makes this so fascinating is the sense of hidden intensity. Behind the dust, matter may be falling inward, radiation may be pouring out, and jets may be forming, yet the visible image stays muted or dark. It is a reminder that concealment is not quietness. A galaxy can hide a raging core behind a carefully placed curtain of cosmic debris. X-rays can expose a violent core buried inside a calm galaxy. Visible light is easily blocked by dust, but X-rays can penetrate regions that would otherwise keep a galactic nucleus hidden. That makes them a powerful tool for discovering activity in galaxies whose centers seem unremarkable at first glance. A system may look like a calm disk or a smooth stellar body, yet X-ray observations reveal a compact, energetic source at the center. Suddenly, the story changes. What seemed quiet becomes a galaxy with a feeding black hole, hot surrounding material, or both. This is one of the reasons active galaxies are so compelling. They reward deeper ways of looking. Each wavelength reveals a different layer of reality, and X-rays are especially good at catching high-energy processes close to the central engine. The effect is almost detective-like. A galaxy keeps its secret in ordinary images, then betrays itself in a harsher kind of light. Beneath the serene appearance is a core where matter is being driven to extremes of heat and violence. A galaxy can seem peaceful while its center devours everything nearby. That contrast is one of the most unsettling and fascinating things in astronomy. The outer regions of a galaxy may contain calm old stars, graceful spiral structure, or smooth diffuse light that suggests deep stability. Meanwhile, at the very center, gas clouds, dust, and even disrupted stars can be drawn inward toward a supermassive black hole. The process is not usually dramatic in the sense of everything being swallowed at once. It is selective, ongoing, and often hidden, which somehow makes it more eerie. A galaxy can present a composed exterior, while its heart remains a site of appetite and transformation. This idea matters because it changes the way we imagine galactic life. A serene appearance does not guarantee a passive core. In some systems, the most consequential event is happening in a region tiny compared with the whole galaxy. The outer beauty and the inner hunger coexist. One is broad and visible. The other is concentrated and far more dangerous. Black hole jets can heat gas and stop new stars forming. The influence of an active nucleus does not end near the black hole. Jets and energetic outflows can pump energy into the surrounding gas, making it harder for that gas to cool and collapse into new stars. This is one of the most important ideas in galaxy evolution, because it offers a way for a central black hole to regulate the future of the host system. A galaxy might have plenty of gas in a broad sense, yet if that gas stays too hot or too stirred up, star formation can fade. In this way, the central engine acts less like a simple light source and more like a control mechanism. What makes this so remarkable is the reach of the effect. A process born near the very center can shape the destiny of the whole galaxy. The same black hole that feeds on inflowing matter may also help shut down the next generation of stars. Creation at the core can lead to quietness on larger scales. Strange galaxies often show a battle between growth and shutdown. Many galaxies do not sit comfortably in one mode or another. Instead, they seem caught between competing processes. Gas may be flowing inward and feeding the central black hole, while outflows or jets push energy back into the surrounding medium. Star formation may flare in one region and fade in another. A merger might deliver fresh material at the same time that feedback begins to disrupt or heat it. This tension is part of what makes strange galaxies so fascinating. They feel unstable in a meaningful way, as though different futures are contending inside the same system. Growth is possible, but so is suppression. The outcome depends on how matter moves, where energy is deposited, and how long each phase lasts. From a distance, a galaxy can look like a single object. In reality, it may contain a struggle between accumulation and restraint. We are not only seeing what a galaxy is, we are seeing the forces that determine what it will be allowed to become. A galaxy's central black hole can shape its whole future. For something so compact, a supermassive black hole can have astonishing influence. Its mass correlates with properties of the host galaxy, especially the central bulge, which hints at a long shared history. More dramatically, the energy released when the black hole feeds can affect how gas behaves across much larger scales. If the nucleus remains active, it may drive winds, launch jets, or heat surrounding material enough to limit future star formation. If it quiets, gas may cool and other processes can dominate. This makes the black hole seem less like a passive object tucked away in the center and more like a participant in the galaxy's evolution. The fascination comes from scale reversal. A region small beyond imagining compared with the galaxy may still help determine whether the larger system keeps growing, changes character, or settles into a more dormant life. It is one of the clearest examples in astronomy of how a tiny center can influence an enormous whole. Some galaxies have cores that switch on and off. Not every active nucleus remains steadily brilliant over cosmic time. Evidence suggests that some galactic cores pass through cycles of activity, with episodes of feeding and radiance followed by quieter intervals. A galaxy may blaze as an active nucleus when enough material reaches the black hole, then dim when that supply falls off or conditions change. Later, another inflow might revive the core. Astronomers can sometimes infer these on and off phases from structures left behind, such as extended emission that outlasts the brightest activity or inconsistent signs across different wavelengths. This is fascinating because it makes a galactic center feel intermittent rather than fixed. The core is not always in the same state. It can flare into prominence, fade from view, and perhaps awaken again. That changing behavior also helps explain why galaxies that seem similar overall may have very different hearts at the moment we observe them. A strange galaxy can be caught during one brief chapter in a much longer, stop-start central life. Even one hidden black hole can rewrite a galaxy's story. A black hole does not need to announce itself loudly in visible light to matter. If it is feeding behind dust, emitting in hard-to-see wavelengths, or only briefly active, it can still change how a galaxy evolves. It may stir gas, launch a subtle outflow, alter central dynamics, or regulate future star formation in ways that become clear only later. This is why astronomers are so careful about hunting for buried nuclei. Missing one means misunderstanding the galaxy around it. The appeal of this idea is that it turns the center into a source of hidden authorship. The galaxy's shape, color, and stellar population may all carry the consequences of an engine that is not obvious in a simple image. A story that seemed to be about mergers, dust, or ordinary aging may need to be rewritten once the concealed black hole is recognized. Strange galaxies often become stranger in that moment. A secret in the core suddenly explains the larger life around it. The weirdest galactic hearts are brightest where space looks darkest. The centers of active galaxies often appear wrapped in shadow. Dust lanes, obscuring material, and the sheer contrast with surrounding darkness can make those regions look visually dense and mysterious. Yet that is where some of the universe's most powerful processes are underway. Matter is spiraling inward, temperatures are rising, magnetic fields are shaping jets, and radiation is being generated on staggering scales. The darkness is not emptiness. It is the threshold around an engine. That reversal is part of what gives strange galaxies such depth. The places that seem most concealed can also be the most intense. Astronomers learn to read that darkness differently, not as absence, but as a sign that some of the light is hidden, redirected, or emerging in forms our eyes cannot naturally catch. A galactic heart can look dark because the view is difficult, not because nothing is happening. In some of the strangest systems, the most brilliant truth lies exactly where the visible scene seems hardest to penetrate. Lenticular galaxies sit mysteriously between spirals and ellipticals. They have the flat disks of spiral galaxies, yet they lack the sweeping arms that usually make a spiral so easy to recognize. At the same time, they can look smooth and settled in a way that brings ellipticals to mind. That in-between quality is what makes lenticular galaxies so intriguing. They seem to occupy a middle ground, as though they are caught between one identity and another. Some may be former spirals that lost or used up the gas needed to sustain bright spiral structure and ongoing star formation. Others may have been shaped by dense environments where repeated interactions stripped away material and softened their appearance. What remains is a galaxy that still remembers the disk it once emphasized, but no longer displays the full flourish of spiral life. They feel like transition made visible. When you look at one, you are not just seeing a category. You are seeing a question about what kind of history can erase a pattern without destroying the whole underlying form. Some galaxies lost their spiral arms but kept their disks. That is one of the strangest transformations in galactic astronomy, because it suggests that a familiar shape can fade without the whole structure falling apart. A spiral arm is not a rigid object. It is a pattern tied to motion, density, gas, and star formation. If the gas is stripped away, heated, or consumed, the bright young stars that help define the arms can vanish over time. The disk remains, still broad and flat, but its once vivid structure softens into something smoother and quieter. This makes certain galaxies feel haunted by a former self. The architecture is still there, but the flourish is gone. Environments rich in hot gas, crowded galaxy clusters, or earlier encounters may all help drive that change. What fascinates astronomers is that the galaxy does not become unrecognizable all at once. It lingers in a halfway state. You can still see the disk that once carried more dramatic patterns, even after the grand design has largely drained away. Elliptical galaxies can be smooth on the outside and violent within. At first glance, an elliptical galaxy can seem almost serene. Its light is spread in a rounded glow, without obvious spiral arms, dust lanes, or dramatic clumps. But that calm appearance can be deceptive. The stars inside are not moving in one simple ordered plane as they do in a disk. Instead, they may travel on many different orbits, creating a far more complex internal dynamical state. In some ellipticals, hot gas fills the system and shines in X-rays, revealing an environment of enormous energy. A placenta, a supermassive black hole, may still be influencing the galaxy's future. And the galaxy's smooth body may itself be the aftermath of ancient mergers violent enough to erase older structure. This is why ellipticals are so compelling. They look settled, yet their very smoothness may be the product of turbulence, mixing, and repeated upheaval. The outside gives you no hint of the intense history and restless internal motion concealed within that soft luminous shape. Giant elliptical galaxies often form from repeated ancient mergers. The largest ellipticals in the universe did not usually arrive in their grand, smooth form by growing quietly in isolation. Evidence points instead to a long history of collisions and absorptions. Smaller galaxies merged, then larger ones merged again, until the resulting system became immense, rounded, and rich in old stars. Each event stirred stellar orbits, diluted earlier structure, and built a more massive whole. Over time, repeated mergers could create the giant ellipticals seen at the centers of galaxy clusters, where they often dominate their surroundings like monarchs of accumulated history. What makes them so fascinating is that their present calm hides a layered ancestry of captures and reshaping. They look unified now, but that unity may be the final product of many different galaxies folded together over billions of years. A giant elliptical can be imagined as a city built from the stones of older cities, so thoroughly remade that the original streets have vanished, yet traces of every past construction still linger in its mass. Some ellipticals contain surprisingly little cold gas for new stars. That absence matters because cold gas is the raw material from which new stars are made. Without much of it, a galaxy's future becomes quieter. Elliptical galaxies are often dominated by older reddish stars, and one reason is that many of them have very limited supplies of the cool, dense gas needed to keep star formation going. The question is not only where the gas went, but why it failed to return in usable form. Heating from past activity, environmental stripping, and feedback from central black holes may all play a role. The result is a galaxy that shines beautifully while making very little that is new. This gives ellipticals a distinct mood in cosmic terms. They can be grand, massive, and luminous. Yet much of that light comes from ancient stars rather than recent creation. What makes this so striking is the contrast between scale and stillness. A huge galaxy can exist in a state that feels almost retired, bright with history, but poor in fresh beginnings. Others hide shells and ripples from past galactic collisions. Not every elliptical galaxy is perfectly smooth when you look closely enough. Some reveal faint arcs, nested shells, or ripple like features in their outer light. These are among the most beautiful clues in galactic archaeology because they preserve evidence of a past encounter long after the main violence has subsided. Such structures can form when a smaller galaxy falls into a larger one and its stars begin to spread out along particular orbits. As those stars slow and pile up at certain distances, they create delicate shell patterns that appear like frozen waves around the host galaxy. The effect is subtle, which only makes it more alluring. A galaxy that first seemed featureless begins to reveal hidden texture, and that texture turns out to be memory. Shells and ripples show that smoothness is not always simplicity. Sometimes it is a surface draped over an eventful past, with just enough faint structure remaining to whisper that another galaxy once entered, dissolved, and left its mark. Shell galaxies preserve old impacts like frozen splashes in starlight. The resemblance is uncanny. Around certain galaxies, faint arcs appear one beyond another, as though light itself had been tossed outward in a series of expanding waves and then stopped in place. These shell structures are thought to form during mergers, especially when a smaller galaxy plunges into a larger one and its stars are scattered onto elongated paths. As those stars reach the outer parts of their orbits, they bunch up and create luminous edges that read as shells. The result is both elegant and eerie. A past impact is preserved not as rubble, but as geometry. What makes shell galaxies especially captivating is the sense of delayed revelation. The collision may have happened long ago, yet its signature remains visible in these delicate layered traces. They are the opposite of a dramatic wreck in progress. They are the afterimage of an old event, still hanging in starlight. You look at them and feel that time in astronomy does not erase everything. Sometimes it arranges the evidence beautifully. A smooth galaxy can still hold a very messy past. Astronomical appearance can be wonderfully misleading. A galaxy may present a rounded, polished, seemingly settled face, and yet that calm exterior can be the product of ancient disruption rather than peaceful growth. Mergers, accretion events, and repeated close encounters can scramble earlier structures so thoroughly that the final result looks simple. Dust may disperse, young blue stars may fade, and obvious tidal features may weaken until only a smooth glow remains. But hidden inside are the consequences of all that complexity. Stars may move on mixed orbits. The halo may contain streams from consumed companions. The central black hole may have grown through old feeding episodes tied to past interactions. This is part of what makes galaxy evolution so compelling. It teaches us not to confuse surface order with quiet history. A galaxy can look composed because time has blended its disruptions into one coherent body. Smoothness, in that sense, is not always innocence. Sometimes it is what cosmic turbulence looks like after enough years have passed. Strange shapes often survive long after the collision is over. A close encounter between galaxies may end, but the distortions it creates can linger for immense periods. Tidal tails, warped disks, shells, off-center rings, and unusual streams of stars do not vanish the moment the main interaction concludes. They can remain as long-lived signatures of what happened, allowing astronomers to reconstruct events that are already deep in the past. This persistence is one of the reasons strange galaxies are so valuable. They're like archives written into structure. Even after the participants have merged or moved apart, their former relationship may still be legible in the surviving oddities. The universe is patient with its clues. It leaves debris, asymmetry, and disturbed motion in place long enough for later observers to study them. That means a galaxy can still look peculiar, even when the cause of that peculiarity is no longer obvious at first glance. Strange forms are not always signs of something happening now. Sometimes they are old consequences that have simply refused to fade. The calmest galaxies may be the aftermath of cosmic violence. This is one of the deepest reversals in the subject. A galaxy that seems placid, rounded, and settled may owe that very appearance to ancient collisions violent enough to destroy earlier order. Repeated mergers can erase disks, mix stellar orbits, and smooth away many obvious signs of disturbance. What remains may look quiet not because nothing dramatic occurred, but because the drama finished long ago and the remnants blended into a stable whole. That possibility changes the way we see calm galactic forms. Instead of reading them as untouched, we begin to read them as resolved. Their stillness becomes the final chapter of a loud story. This is why strange galaxies lead naturally into ordinary-looking ones. The line between them is not always firm. A bizarre wreck in one era can become a graceful giant in another. The calm is real, but it may have been earned through upheaval. In astronomy, serenity is sometimes the polished surface left behind by enormous ancient force. Some galaxies spin around cores that rotate in another direction. That is not a poetic exaggeration. Astronomers have found galaxies in which the central region rotates one way while the outer parts rotate another, or where distinct kinematic components move in opposing directions. This is one of the clearest signs that a galaxy's history involved outside interference. Material acquired from a merger or a captured companion can settle in ways that preserve its original angular momentum, creating a core whose motion no longer matches the rest of the system. What makes this so fascinating is that the galaxy may not look unusual in an ordinary photograph. The real strangeness is hidden in the motion of its stars and gas. It is revealed only when astronomers split the light and measure how different regions move. Then the galaxy stops being a static image and becomes a layered story of assembly. A mismatched core is like a memory, still spinning inside the body. It tells us that the galaxy did not grow as one seamless thing. Counter-rotating stars reveal that galaxies can steal outside material. In some galaxies, one population of stars circles in one direction while another circles the opposite way. That is a deeply strange arrangement, because it suggests the galaxy did not form all its stars from one well-behaved rotating disk. Instead, outside material must have been added later, bringing its own angular momentum with it. Gas captured from a passing galaxy can settle into reverse motion and then form stars, preserving that acquired direction. A merger with another system can do something similar on a larger scale. The result is a galaxy that carries two histories at once, written into stars moving against one another. What makes this so captivating is the clarity of the clue. Motion becomes evidence of theft. A galaxy that once seemed self-contained turns out to have been taken from its surroundings. Counter-rotation is one of the most elegant signatures of that process, because it does not rely on shape alone. It turns the invisible memory of acquisition into something astronomers can measure directly. A galaxy can contain two disks moving against each other. This is one of those facts that feels impossible until you realize how patient and layered galaxy growth can be. A disk galaxy usually suggests one broad rotating system, with stars and gas sharing a common direction. Yet some galaxies contain two distinct disk-like components that revolve in opposite directions. One may have formed first, while the other was built later from captured gas that settled into reverse motion before producing new stars. The image is extraordinary. Inside what seems like a single galaxy, two stellar systems are sliding past one another with opposite spins. The structure is stable enough to last, yet strange enough to reveal a very unusual past. It is hard to imagine a better example of a galaxy as an assembled object rather than a single birth event. These opposing disks show that a galaxy can grow by addition without fully bending the motion of what it acquires. The result is not chaos, but an enduring internal contradiction. Strange rotation is a clue that a galaxy had company. A galaxy left entirely alone for long enough might still be complex, but some of the oddest rotational patterns strongly suggest interaction with others. Misaligned gas, counter-rotating components, and decoupled cores are hard to explain without some outside contribution. They imply that material arrived from elsewhere, or that a merger disrupted the original motion and left behind a more complicated arrangement. In that sense, strange rotation is social evidence. It tells us the galaxy did not spend its life in isolation. What makes this so appealing is that the clue is subtle. There may be no great tidal tail or obvious collision scar visible any longer. The shape may even look calm. Yet the internal motion preserves the fact that another galaxy once mattered deeply. Astronomers read these patterns the way historians read traces in a document. A hidden relationship becomes visible through what does not rotate as expected. Motion reveals companionship after shape has forgotten it. Warped galaxies show that gravity keeps tugging long after a merger. A galactic disk can look like a flat record from a distance, but many are bent, twisted, or lifted at the edges. These warps are especially fascinating because they show that a galaxy's outer structure remains vulnerable long after a major encounter seems finished. A past merger, the pull of a companion, or the influence of an uneven dark matter halo can all keep the disk from settling into a perfect plane. The result is a galaxy that looks subtly bent, as if some invisible hand has not quite let go. What makes warps so compelling is their persistence. They are often not catastrophic distortions. They are lingering tugs made visible. Even a relatively small interaction can leave an imprint on the outskirts, where gravity's hold is weaker and the structure is easier to disturb. A warped disk reminds us that galaxies are not rigid objects. They are responsive and pliable on large scales, still adjusting to events that may be long past. Some galactic disks bend like records left in the heat. It is a wonderfully earthly comparison for a deeply cosmic phenomenon. The broad disk of a galaxy can look slightly bent upward on one side and downward on the other, producing a shape that feels familiar in an oddly domestic way. But the cause is not heat in any simple sense. These bends arise from gravitational influence, from old interactions, or from the way incoming material settles into the system over time. Because the outer parts of a galaxy are less tightly bound than the inner regions, they can be especially vulnerable to being tilted or twisted. What makes these warped disks so memorable is their mixture of delicacy and scale. The bend may seem modest, yet it affects a structure spanning tens of thousands of light years. A tiny-looking deviation in an image corresponds to a huge rearrangement of matter in space. The galaxy remains recognizable, but not quite orderly. It is as though the universe has pressed a thumb against its edge and left it slightly out of true. A galaxy's shape can twist because dark matter guides it. Dark matter cannot be seen directly, yet its gravity helps determine how galaxies move and settle. If a galaxy sits inside a dark matter halo that is not perfectly aligned with the visible disk, the ordinary stars and gas may respond over time in ways that produce twists or warps. This is one of the great fascinations of galactic structure. A visible shape may be partly controlled by something invisible surrounding it. The stars are not only reacting to one another and to gas, they are also moving within a larger gravitational framework that does not shine. That means the odd geometry of a galaxy can become a clue to the form and influence of hidden matter. What makes this especially compelling is that it turns shape into indirect evidence. A twist in the disk is not just a visual quirk. It may be the visible consequence of an unseen architecture. In that sense, strange galaxies are often teaching us about forces we cannot photograph directly. Even invisible mass can leave visible scars in starlight. That idea lies at the heart of much modern astronomy. Dark matter does not glow, yet its gravity shapes the motion of stars, the structure of disks, and the outcome of galactic interactions. If its distribution is uneven, or if a galaxy is embedded in a halo with particular properties, the visible matter can respond in ways that leave observable signatures. Warps, unexpected orbital patterns, and distortions in extended structures may all carry the imprint of this hidden mass. What makes the concept so gripping is the indirectness of it. Astronomers are often reading effects rather than seeing causes. The scar is visible. The thing that made it is not. This lends strange galaxies a detective story quality. Their oddness becomes evidence in a case built from consequences. A star stream may curve in a certain way. A disk may bend more than visible matter alone would suggest. Each such feature hints that an unseen player has helped shape the scene. Strange galaxies help astronomers map matter they cannot directly see. Because their structures and motions are unusual, strange galaxies often act like experiments provided by nature. A warped disk, a polar ring, a counter-rotating core, or an unexpectedly diffuse system can all reveal how mass must be distributed if the observed behavior is to make sense. In that way, these galaxies become tools for studying dark matter and hidden gravitational influence. Ordinary galaxies help too, of course, but the strange ones often give extra leverage because their odd configurations are especially sensitive to the underlying mass. They are like test particles on grand scales, tracing out the invisible framework that holds them. This is one reason astronomers treasure them. Their weirdness is not a distraction from deeper understanding. It is the route toward it. When a galaxy behaves in a surprising way, researchers are forced to ask what unseen structure could allow that behavior. The answer often points beyond the visible stars to a much larger hidden scaffold surrounding and guiding the system. Their weird motions often make more sense than their shapes. A galaxy can look baffling in an image. It may seem lopsided, bent, or oddly assembled in ways that resist easy interpretation. Yet once astronomers measure how its stars and gas move, the mystery can sharpen into something surprisingly coherent. Rotation curves, velocity maps, and spectral shifts often reveal the logic behind the strange appearance. What looked chaotic may turn out to be the aftermath of a merger, the result of acquired material settling into a new plane, or the signature of a warped disk responding to hidden mass. This is one of the great pleasures of galactic astronomy. Motion can rescue meaning from shape. A picture alone may leave you with questions, but kinematics can show how the parts belong to one story. Strange galaxies are especially rewarding in this way because they remind us that appearance is only the surface. To really understand them, you have to let them move. Once they do, many of their oddest forms begin to feel almost inevitable. The earliest galaxies already looked stranger than expected to astronomers. For a long time, many people imagined the early universe would reveal simple beginnings, small young galaxies slowly growing into the grand forms we know today. But when astronomers looked deeper, some of those ancient systems already seemed surprisingly unusual. They appeared bright, compact, clumpy, and in some cases more developed than older models had comfortably predicted. Instead of a neat opening chapter, the early universe began to look busy, inventive, and hard to summarize. That is part of what makes these first galaxies so thrilling. They remind us that cosmic history did not unfold in a plain, orderly line. Structure emerged under intense conditions, with gas collapsing, stars forming, and matter gathering on timescales that still challenge explanation. The strange galaxies of deep time do not feel like rough drafts of later ones. They feel like bold early experiments. Even near the dawn of galactic history, the universe seems to have been trying out forms and behaviors far more varied than astronomers once expected. Young galaxies in the early universe were trumpy, chaotic, and bright. The farther astronomers look into space, the farther back they look in time. In that distant era, many galaxies did not resemble the elegant spirals and smooth ellipticals that feel so familiar today. Instead, they often appeared patchy and irregular, with bright knots of intense star formation scattered through them like islands of activity. Their shapes could seem unsettled, as though gravity had not yet had time to organize everything into cleaner forms. But that disorder is exactly what makes them so captivating. It shows galaxies during a more turbulent youth, when gas was abundant, mergers were common, and stars were being born in vigorous, concentrated bursts. These were not quiet systems waiting politely to mature. They were active, luminous, and structurally restless. Looking at them feels a little like opening an old family album and finding that the earliest pictures are the wildest ones. The young universe did not begin with composure. It began with galaxies full of bright, uneven energy. Some ancient galaxies formed stars much sooner than models predicted. That discovery landed with real force because it suggested the early universe may have become productive faster than many astronomers expected. In the standard picture, matter had to gather, cool, and collapse into the first generations of stars and galaxies. That process was always understood to begin early, yet some observations hinted that substantial stellar populations may have built up remarkably quickly. In other words, the cosmos may have started making complex galactic systems with surprising speed. This is fascinating because it touches one of the biggest questions in astronomy. How rapidly can structure emerge after the beginning? If stars formed sooner and in greater numbers than expected in some early galaxies, then models of gas collapse, feedback, and growth may need adjustment. The wonder comes not only from the science, but from the implication. The universe may have wasted no time. In some places, it seems to have moved from darkness toward organized light, with an urgency that still feels astonishing. Webb revealed early galaxies that seemed surprisingly mature, astonishingly fast. One of the most exciting things about the James Webb Space Telescope is that it opened a new window on the early universe. And through that window, some galaxies appeared more substantial than many people anticipated. Certain distant candidates looked bright, structured, and in some cases rich enough in stars to raise immediate questions about how quickly such systems could have assembled. That did not mean every first impression would remain unchanged. Follow-up work, better measurements, and spectroscopy always matter. But the initial shock was real, and it was wonderfully productive. Webb did not simply add more early galaxies to a known picture. It sharpened the sense that the first chapters of galactic history may have been more vigorous and complicated than expected. That is why these observations feel so alive. They do not merely show distant objects. They reopen the argument about how fast galaxies grew up. The early universe, once imagined as simpler, began to look unexpectedly capable of building impressive structures with remarkable speed. The first galaxies may have grown through relentless swallowing and merging. In the young universe, matter was distributed unevenly, and gravity wasted no time exploiting those differences. Small clumps drew in more gas and dark matter. Nearby systems interacted, collided, and combined. Instead of galaxies growing only by steady, quiet accumulation, many may have expanded through repeated acts of capture and merger. That would help explain why some early systems look irregular, active, and structurally unsettled. They were not isolated islands developing at leisure. They were participants in a crowded age of assembly. This picture is deeply compelling because it makes the birth of galaxies feel hungry. Growth did not always happen by gentle addition. It may often have happened by taking in neighbors, tearing them apart, and folding their matter into a larger whole. That same basic pattern continues later in cosmic history, but in the early universe, it may have been especially intense. The first galaxies were not merely born. They were built through competition, encounter, and repeated consumption in a universe still learning how to organize itself. Strange galaxies are clues to how the universe learned structure. A strange galaxy is not just an oddity to admire. It is evidence about process. Whenever astronomers find a galaxy with an unusual shape, motion, or history, they gain a clue about the forces that turn a nearly uniform early universe into the richly structured cosmos we know now. Rings, warps, bursts, mergers, faint diffuse systems, and violently active cores all reveal different ways that matter responds to gravity, gas dynamics, and time. In that sense, strange galaxies are like grammar lessons in the language of cosmic construction. They show how order emerges, how it is disrupted, and how new forms arise from that disruption. This is what makes them so much more than curiosities. They allow astronomers to reconstruct the rules of assembly by studying the exceptions. the dramatic cases, and the forms that refuse to fit neatly into simple categories. A strange galaxy feels memorable because it is unusual. It matters because unusual structures often tell us most clearly how the universe built everything else. Looking farther away means watching galaxies become younger and stranger. That is one of astronomy's most beautiful tricks. Because light takes time to travel, distance becomes a kind of time machine. Nearby galaxies show us later chapters of cosmic history. More distant ones show us earlier chapters, when galaxies were younger, less settled, and often more unruly. This is why the deep universe can feel increasingly strange. As you look farther out, you are not just seeing fainter objects. You are seeing a cosmos in which familiar structures were less mature and the pace of change was often more intense. Galaxies appear clumpier, interactions may be more common, and the distinction between neat categories can blur. The farther we see, the less the universe resembles the calm atlas of modern forms. That progression is profoundly exciting because it lets astronomers watch galactic history unfold in reverse. The elegant systems of today give way to rougher ancestors, as though the universe is slowly shedding polish the deeper into time we look. Distance becomes a journey into strangeness. Some distant galaxies appear stretched by gravity from objects before them. Sometimes a galaxy looks odd not because of its own structure, but because something massive lies between it and us. A foreground galaxy or cluster can bend space-time strongly enough to distort the light of a background galaxy, stretching it into arcs, smears, or elongated shapes. This is gravitational lensing, and it creates some of the most uncanny sights in astronomy. A normal distant galaxy can appear warped into a form that seems almost impossible, until you remember that light itself is traveling through curved space-time. What makes this so enthralling is that the distortion carries information. The amount and pattern of stretching reveal the mass of the intervening object, including the dark matter we cannot see directly. So, a distant galaxy may appear strangely drawn out for two reasons at once. It is being magnified, and it is helping map invisible mass. The weirdness is not an error in the sky. It is gravity making geometry visible across enormous distances. Gravitational lensing can turn one galaxy into arcs, rings, or mirrors. This is one of the universe's most elegant optical illusions, except that nothing about it is false. When a massive object sits along the line of sight to a more distant galaxy, its gravity bends the background light. If the alignment is just right, the result can be extraordinary. A single background galaxy may appear as multiple images, curved arcs, or even a near-complete ring of light around the foreground mass. These features can look like deliberate art, yet they are natural consequences of general relativity working on a vast scale. The fascination lies in the combination of beauty and usefulness. Lensed galaxies are not only spectacular, they allow astronomers to study very distant objects in amplified form and to infer the mass distribution of the lens itself. A galaxy becomes both subject and tool. The same event that distorts its appearance can make it easier to study. The sky turns into an instrument, and space-time itself becomes part of the telescope. Sometimes a strange galaxy looks weird because space-time bends its light. That idea changes the way you look at the universe. Not every bizarre shape belongs entirely to the object being observed. In some cases, the strangeness comes from the path the light took on its way to us. Massive objects curve space-time, and light follows those curves. So a distant galaxy may appear bent, duplicated, elongated, or wrapped into a partial ring, not because it is physically shaped that way, but because its image has been transformed by gravity in between. This is one of the most profound lessons in astronomy. Appearance is not always local. The cosmos between us and a galaxy can participate in the picture. That makes the universe feel less like a simple collection of objects and more like an interconnected field of influence. A strange image can be telling two stories at once, one about the background galaxy and one about the hidden mass along the line of sight. The weirdness belongs to space-time as much as to the distant source. There are galaxies with almost no dark matter, and that is baffling. Dark matter is usually treated as one of the basic ingredients of galaxies, especially when astronomers explain how stars remain bound and how structures formed in the first place. That is why reports of galaxies with surprisingly little dark matter caused such interest. If confirmed in particular cases, such systems challenge the assumption that visible matter always sits inside a substantial dark matter framework in the usual way. They raise difficult questions. Were these galaxies stripped by interactions, leaving the stars behind but removing much of the hidden mass? Did they form under unusual conditions? Or are the measurements telling a more complicated story than first believed? What makes this so gripping is that the exception strikes at a central idea. A galaxy with very little dark matter feels almost like a contradiction in modern cosmology. Even a small number of such objects matters because they force astronomers to test how universal their models really are. Strange galaxies become most valuable when they make familiar theories uncomfortable. Others seem almost entirely ruled by dark matter's hidden pull. If some galaxies appear deficient in dark matter, others seem drenched in it. In these systems, the visible stars may be sparse or faint, yet their motions imply a much stronger gravitational field than the luminous matter alone could provide. Dwarf spheroidal galaxies around the Milky Way are famous examples, because they contain relatively little visible material compared with the apparent mass needed to keep them bound. This makes them some of the best places to study dark matter's influence in a direct dynamical sense. What is so fascinating here is the inversion of what we instinctively value. The stars may look meager, almost incidental, while the real story lies in the unseen mass dominating the system's behavior. These galaxies are like small, visible hints embedded in a much larger, invisible reality. Their importance comes precisely from how little they seem to show. The faintness of the light only sharpens the mystery, because it tells us that most of what matters there cannot be seen at all. Some galaxies stopped growing stars and became cosmic graveyards. There is something haunting about a galaxy that still shines, yet no longer makes many new stars. Its old stellar population continues to glow, but the process that once refreshed it has largely ended. The gas may have been consumed, heated, stripped away, or prevented from cooling by feedback from the central black hole or the surrounding environment. Whatever the cause, the result is a galaxy whose active era has faded. Astronomers sometimes call such systems quenched, which is a wonderfully apt word. The fire has not gone out in the sense of total darkness, but the vigorous cycle of new star formation has been extinguished. This is compelling because it gives galaxies a real-life history. They are not static ornaments. They have phases of growth, upheaval, and decline. A cosmic graveyard is still beautiful, yet the beauty has changed in character. It is no longer the brightness of youth. It is the quieter light of a place living on after its most creative days are done. Dead galaxies can still shine beautifully with ancient red starlight. A quenched galaxy is not empty, and it is certainly not dark. What remains is often a grand concentration of older stars, many of them cooler and redder than the hot blue stars that dominate active star-forming regions. This gives some old galaxies a warm reddish glow that can feel almost dignified. Their beauty is different from the spark of youthful systems. It is steadier, softer, and marked by age. That contrast is part of what makes them so moving to think about. Even after a galaxy stops making many new stars, it continues to carry the light of countless earlier generations. The brilliance you see may be the accumulated shine of stars that have endured for immense spans of time. In that sense, a dead galaxy is not lifeless in any simple way. It is full of stellar survivors. The color itself becomes a clue to history, telling you that the galaxy's great age is not hidden. It is written gently across the whole glow. A galaxy can survive after losing the gas needed for life-giving stars. This is one of the striking differences between galaxies and living things. A galaxy can lose the material needed for future creation and still persist for billions of years as a coherent structure. Stars already in place continue orbiting. The overall shape may remain stable. The galaxy still shines, still carries mass, still influences its surroundings. What changes is its future potential. Without enough cold gas, the birth of new stars dwindles or stops. That makes the galaxy feel altered but not erased. It has survived, though in a quieter state. This is fascinating because it reminds us that galaxies are durable beyond ordinary intuition. They can be stripped by cluster environments, exhausted by bursts of activity, or reshaped by feedback, and yet the stellar system itself endures. The loss is not immediate destruction. It is more like the closing of one chapter. The galaxy continues onward, lit by what it made earlier, while the machinery of renewal falls still. Strange galaxies show that beauty in space often follows disruption. Some of the most unforgettable galactic forms are not products of calm. Rings, tidal tails, shells, arcs, warped disks, and luminous bursts of star formation often arise because something has been disturbed, struck, absorbed, or pulled apart. That gives strange galaxies a wonderful emotional texture. Their beauty is not separate from their violence. It comes through it. A graceful ring may mark an impact. A delicate shell may preserve the memory of a consumed companion. A brilliant central glow may reveal a black hole feeding after gas has been driven inward. This is one reason strange galaxies feel so compelling to people who are new to the subject. They overturn the idea that order and elegance always come from quiet conditions. In the universe, some of the loveliest structures are aftermaths. They are patterns left by collision, imbalance, or intense transformation. The sky teaches this lesson again and again. Disruption is not only destructive, it can also become the source of forms so striking they seem almost designed. The universe builds its oddest galaxies through collision, hunger, and time. Those three ideas run through the whole subject like hidden threads. Collision reshapes galaxies, drawing out tails, forming rings, and scrambling old structures into new ones. Hunger drives gas inward, feeding black holes and igniting bursts of star formation that can transform the core and alter a galaxy's fate. Time then works over everything, preserving some scars, softening others, and turning violent episodes into apparently settled forms. Taken together, these forces explain much of the richness we see in strange galaxies. They do not arise from one cause alone. They are products of repeated encounters, of matter seeking deeper wells of gravity, and of long ages allowing consequences to accumulate. That is what makes the universe feel so creative here. It is not building with a careful, fixed plan. It is building through process, through pressure, through repeated change. The oddest galaxies are often the ones that display those processes most clearly, as though the hidden machinery of cosmic history has briefly become visible in their shape. Every weird galaxy is a record of forces too large to imagine. A strange galaxy may look like a curiosity in a photograph, but behind that image lies a scale of action that resists ordinary intuition. tails stretch across distances greater than whole galaxies. Black holes affect matter from compact central regions with astonishing power. Dark matter halos guide motion through invisible mass on vast scales. Mergers unfold over spans so long that human history disappears into nothing beside them. To study a weird galaxy is therefore to confront force in a form that exceeds daily thinking. Gravity is no longer a falling object or a planet in orbit. It becomes the architect of structures spanning tens or hundreds of thousands of light years. This is part of why the subject feels so profound. Every odd form is evidence that something immense happened, whether a collision, a feeding event, a tidal distortion, or a hidden gravitational influence. The galaxy becomes a record, and its weirdness is the handwriting of powers so large that the mind can only circle them in awe. The stranger a galaxy looks, the more history it may be hiding. A bizarre shape is rarely random. It usually means something happened, and often more than one thing. A warped disk suggests tugging forces or past accretion. A shell hints at a swallowed companion. A bright active core points to matter driven inward. A faint diffuse body may preserve a very different evolutionary path from a dense luminous one. Strange appearance becomes an invitation to ask what sequence of events could have produced it. That is why weird galaxies are so satisfying. They reward curiosity with narrative depth. The stranger the form, the stronger the suspicion that the object has lived through encounters, transitions, and structural rearrangements not immediately obvious from a first glance. In that sense, oddness is often historical richness made visible. A galaxy with an unusual look may be carrying several chapters of cosmic memory at once. Instead of hiding its past completely, it leaks the past through shape. The visual strangeness is not noise. It is biography written into matter and light. To study strange galaxies is to watch the universe experimenting with itself. That may be the most enchanting truth of all. Strange galaxies show that the cosmos is not a static display of repeated forms. It is a place where matter, gravity, radiation, and time combine in endlessly varied ways. Some experiments produce rings. Some produce jets. Some produce ghostly diffuse systems, hidden dark-dominated dwarfs, or giant smooth remnants built from many old collisions. The value of these galaxies is not only that they are unusual, it is that they reveal possibility. They show what can happen when familiar ingredients meet under unfamiliar conditions. In doing so, they make the universe feel less like a finished arrangement and more like an ongoing process of trial, consequence, and transformation. That is why they are so captivating to follow. Each one hints that reality is wider than our first categories. To look at them is to see nature trying structures, pushing patterns, and exploring outcomes across cosmic time. The weird galaxy becomes a sign that the universe is still astonishingly inventive. As we come to the end of our journey through strange galaxies, we have drifted past rings of stars, torn tails of light, hidden black holes, ghostly systems, and ancient collisions still written across the dark. We have seen that galaxies are not always calm islands of stars. Some are warped. Some are blazing. Some are nearly invisible. And some carry the deep marks of meetings that changed them forever. The universe can seem still from far away, yet tonight it has revealed itself as restless, creative, and full of astonishing forms. And now, perhaps, those great and distant shapes can begin to soften in the mind. The bright rings can dim. The long tidal streams can stretch away into the dark. The crowded cores and hidden jets can grow quiet, until all that remains is the feeling of vastness and the slow hush of space. Thank you for spending this time here with me on the Sleepy Science channel. And if you enjoyed this journey through the stranger corners of the cosmos, I hope you will subscribe, Leave a thought below or return for another bedtime voyage soon. And if you happen to still be awake in a few moments, there will be another video waiting for you on screen, ready to carry you a little farther into the night. But for now, let your breathing slow. Let your thoughts grow lighter. Let the last of these distant galaxies fade gently into the background as rest draws a little closer. Sleep well, and good night.